Now that we finished investigations 1 and 2, we're going to be exploring more about the relationship between scale factor, perimeter, area, and side lengths. And we're going to do that through a manipulative called reptiles. So let's learn more about what reptiles are. So to begin, what is a reptile? So no, we're not talking about any snakes or lizards today. We are talking about a specific tool, and specifically this is a figure that can be used to create a larger, similar version. And so each of these shapes that you see here by the side, A, B, C, D, is a shape that we can make from reptiles. And so I can actually take A and I can divide A into 4 similar triangles that have the same shape but a different size in comparison to A. I can do the same thing with B. I can divide B into 4 equilateral triangles that just look like B, only smaller. I can do the same thing with C. And if you're not marking those in, I would go ahead and sketch those in so you can see them. And I can do the same thing with D. And so I should be noticing here that I'm making these shapes, again, that are similar to the larger shape, but they allow me to kind of see a special relationship when it comes to things like side lengths, area, and perimeter. So now I'm going to explore what's the scale factor from the original to the larger figure. And I'm going to pull out the shape on A for a minute. So looking at A, if I've just pulled out one of the reptiles by itself, so I'm pulling out kind of like this piece right here, I'm going to compare this to the larger figure. And so this allows me to see that the base of that original is 2 and the height is 3. In comparison to the larger shape, the base is 4 and the height is 6. And so based on what I know about scale factor, I know that I need to be able to multiply corresponding sides by the same number. And so here I know that 3 times 2 would make 6, and 2 times 2 would make 4. So this leads me to realize that the scale factor is 2 when I'm going from the original, the reptile, to the larger figure. Next, I'm going to think about how does the perimeter of the new figure relate to the perimeter of the original. And so if you're looking at this and realizing that the larger figure is doubled, I might be thinking about how perimeter is related to that. So for example, here I can see that my original perimeter, I don't know that exact side length right there, but I can tell that the side lengths are doubling. And I can even just see here that this measurement is extended twice over here. Just like the base has doubled and the height has doubled. And so I'm going to note here that the perimeter has doubled. I don't even have to know the exact perimeter. Again, I'm just kind of thinking about the relationship here. And then I'm going to think about area. And area is a special one because I can think about how many copies of the reptile fit inside of the larger shape. And you'll notice here that all of these fit 4 reptiles inside. However, it is possible to use a different number of reptiles. And you're going to see more of those problems later. But for right now, you should be noticing that I can fit 4 copies of the reptile inside of these shapes. So again, 1, 2, 3, 4 copies here. And so that means that the area from the original, this initial reptile, to the larger shape is quadrupling. Or you could also note times 4, just like above how you could notice it's times 2 to double. Now let's look at a reptile example where it's not just 4 copies within a larger shape. This shape is a rectangle, and we're going to make 16 smaller rectangular pieces within it. So just dividing this into 16 equal-sized reptiles the best that I can. It's not perfect, but it's close. And you can get a sense of this shape here matching with the larger rectangle on the outside. And again, you can make yours a lot more precise than mine. So now we're going to think about the scale factor, and let's just kind of make up some dimensions. Let's say that this rectangle here is 1 on this side here and maybe 2 on the other side. And so if I look at my smaller shape, I'm starting with a 1, for example, on the smaller side. But when I get to my new shape, this has become a side length of 4. And same thing on the other side, I started with a length of 2, but now on my larger figure, I have a length of 2, 4, 6, 8. So 2 to 8. So if I'm looking for a scale factor, again, I'm looking for a number that's going to relate to the corresponding sides. So here I'm going to think about how 1 times 4 would be 4, and 2 times 4 would be 8. So this scale factor would be 4. So now I'm going to think about the perimeter, and if you think about how all of the side lengths are basically quadrupling, right? I'm going from 1 to a side length of 4. I'm going from a side length of 2 over here to a side length of 8. Then the same thing is going to be happening to my perimeter, because again, everything's getting 4 times bigger on the side lengths, and they're 4 times bigger on the perimeter. So you're going to want to talk about how this perimeter is 4 times larger. And again, I can prove that as well by calculating it out if I want to, based on the dimensions I made up. This small rectangle here, based on the dimensions I made, is 2 plus 2 plus 1 plus 1. So I have a perimeter of 6. And my large rectangle is 4 plus 8 plus 4 plus 8. So that's going to give me a perimeter of 24. And again, I can think about how 6 times 4 would make 24. So it's gotten 4 times larger. And now I'm going to think about area. So area, I'm thinking about how many copies of that small reptile fit inside of the larger shape. And so again, if I want to think about how I can now fit 16 copies in here, this area is actually going to be 16 times larger. Another way to prove this would be to find the areas. So for example, I said this small rectangle was 1 by 2, so that is an area of 1 times 2, or 2. And now this area over here of the larger shape would be 4 times 8, which is 32. And so again, you're going to notice it's 2 times 16 would make 32. So this area is 16 times larger. So reptiles really help us to see how many copies of a smaller similar shape can fit inside, and help us clearly see the relationship between area and scale factor. One last thing about reptiles is that they must tessellate. Tessellate basically just means tile. It means that you can tile some shapes together, put them together without having any overlap. So for example, if I was to put together these equilateral triangles, that would be considered a tessellation because they match up and they don't overlap. However, not every shape that tessellates is a reptile. So for example, this over here would be a tessellation. This is a shape you can see that's repeated over and over again, and it's tiled together. However, I can't necessarily put that shape into a similar figure that's larger, like I can with a reptile. So the last thing that's here is a challenge. If you'd like to try it, you're going to try to divide each shape, so A, B, and C, into 4 smaller identical pieces or reptiles that are similar to the original shape. So for example, on A, you're trying to find a way to fit 4 of the same size copies of this type of shape, which is similar to the larger shape of A, within that larger shape. Same thing with B, trying to find 4 copies of this smaller shape that can fit within B. And finally C, again looking for 4 of these smaller shapes to fit within the larger shape of C. So again, if you're having trouble, think back to this equilateral triangle up here about how I made these 4 copies of equilateral triangles fit inside of the larger copy. So go ahead and give it a shot, and then tomorrow be ready to talk about how reptiles connect with scale factor, side lengths,
perimeter and area.